Chapter 7, your last chapter. You're almost done with college algebra. I'm sure you have a big tear. What we're looking at in Chapter 7 are systems of equations. We've looked at linear equations, we've looked at quadratic equations, we've looked at exponential equations, and we're going to look at systems of equations. This is really a concept when there's, as it says at the bottom, when there's more than one thing you don't know. We've been solving for X or solving for Y or solving for whatever, and that's been one variable. So if there was one thing we didn't know, time or whatever it was, cost, we were solving those equations. But let's say we have more than one thing we don't know. Now we have to solve for two different things. And we're going to look at a system of equations to do that. We're going to stick with linear equations for the most part, but that's what we're going to look at. The first lesson here, the first three videos, I guess, I'm hoping, knock on wood, will be somewhat familiar to you. You've probably seen it in the past, but here we go. So solving a system of equations, there's three main ways of doing this, three basic ways of doing this. One is by graphing. One is called the addition method or the elimination method, depending on which text you look at. And one is called the substitution method. So we're going to look at those three different ways. I'm going to start with graphing. Graphing a system of linear equations. So here's an example. I've got Dash, and he's looking at getting some data for his phone, and we have these different plans. So $8 per gigabyte plus a $46 flat rate, or $10 per gigabyte plus $36 for a flat rate. And Dash needs to figure out which contract to use. So graphing is one way to compare these two rates and figure out when they'll be the same. So that's Dash's question here, is when will these plans be the same? We're going to translate these two situations, these two plans, into a linear equation so we can graph it. So $8 per gigabyte plus a $46 flat rate and $10 per gigabyte plus a $36 flat rate would look like this. We'd have 8 times each, so X in this case is going to represent each gigabyte. So it would almost be worth saying 8G, but 8 times X, $8 per each gigabyte plus the $46 flat rate, $10 per gigabyte plus the $36 flat rate. Once you've translated that situation into an algebraic equation, into a linear expression, we can graph those and we can get a visual sense. Graphing is great for getting a visual idea of what's going on in the problem. Oftentimes, graphing doesn't give us very specific information. If the data usage is going to be like 8.2 gigabytes, where that's where they're going to be the same. Graphing is not going to be great for figuring out those fractions and those very, very specific narrowed in pieces, but it's going to give us a great concept of what's going on. So let's take a look. Graphing, we've done lots of graphing in Chapter 3, 4, you did some graphing in Chapter 5. So with a linear expression, the y-intercepts are going to be 46 and 36. So I'm going to start with the top one, y-intercept of 46. I'm going to plot that point on the y-axis. The slope is 8. So I'm going to go rise of 8 to run of 1.
Congratulations.
Sorry, I had a brief interruption there. You saw the solution, but we're still going to go through the graphing. So 46 is the y-intercept, 8 is the slope. Plot the y-intercept, rise of 8, run of 1, and we can connect the dots. There we go. Same thing with the second equation here, y-intercept of 36, and there it is, right about there. And a slope of 10, so we go rise of 10, run of 1, over there. One thing I'm doing, since we're trying to find the point where they intersect, drawing your lines is going to be a lot more important here. Drawing straight lines is going to be a lot more important, because if your line curves off just a little bit and the other line curves off just a little bit, the intersection point, where they come together, where they meet, where they're the same, will vary. And so when I'm doing this, one thing that I'm going to do now that we really need to have an exact point where where these two equations are the same, is I'm going to continue to do this rise over run, because I want to know where is this point where these two equations are the same. At what x value, at what gigabyte are these two equations the same? Where do they intersect? It could be right here at 5 something. However, it's hard to tell. It could be at 4.9. It could be at 5.1. With the graphing, it's a little harder to tell. So if you continue those points along, and you continue that slope, rise over run, rise over run, rise over run, the whole way, there will be a point in any graphing problem that I give you, there will be an exact point where they meet, and it will be an integer point. If there are going to be any fractions or decimals, we won't use graphing for that. So here's the situation. At the point 586 is the point where those two graphs meet, and that's the information we can pull back into Dash. So 5 is going to be the number of gigabytes, and $86 is how much it would cost them for them to be the exact same. At 5 gigabytes, it's the exact same for both of them. How this can also be used is to say, if I'm Dash and I know that I use at least 6 gigabytes every month. Now I'm going to look at this graph a little bit differently. I'm not going to say where are they the same. I'm going to say if I use 6 gigabytes every month and I want to pay the cheapest, well, that purple line, the second equation here, or excuse me, the first equation here with the y-intercept of 46, even though it's more money right away, I know I use at least 6 gigabytes, and so it's going to be cheaper in the end. If I know that I don't use my gigabytes very often, most of the time I'm around Wi-Fi or something, I only use 2 gigabytes a month. Well, then I'm definitely going to go with the second equation here, the second plan. Checking my answer, if I plug 5 back in to the first equation, the first plan, I get $86. I plug 5 back into the second equation, I get $86 again. And so I can check my answer to make sure that it is correct. So again, another method. Graphing is great, again, for getting an idea, and it's great if you have nice integer solutions, but you don't always get an integer solution. So we're going to look at a different method. I believe in this text, it's called the addition method. I will probably refer to it as the elimination method, just because that's what I'm more comfortable with, but it's the same thing. So here's how it works. We've got two equations here, two linear equations. And if you look, the x's and the y's are lined up. That is important for this system to work, for this way of solving this equation, this system to work. You need to have the x's and the y's lined up. So if they're already lined up, this system works really, really well. And here's how we do it. Here's how this process is done. We're going to line those x's and y's up, and we're just going to add. We're going to add the x's together. We're going to combine like terms. We're going to say 2x's plus 4x's, 6x's, and 3y's minus 3y's, or really 3y's plus a negative 3y, because this is like a negative 3. 3 plus negative 3 is 0. So it's called the addition method because you're adding. It's called the elimination method because at some point, the purpose of this method is to eliminate one of the variables. 3y minus 3y is 0. There's no more y's. The y's are eliminated. And 18 plus 30 is going to give me 48. So by combining those two equations together, those two linear equations together by addition, I've eliminated one of the variables. And now it's a really easy equation to solve. I can divide both sides by 6. X is 8. I've solved for x. I'm halfway there. I still need to figure out what y is. So I've solved for x. I've figured out what x is, but I still need to figure out what y is. At this point, I can choose either one of these equations, because in both of these equations at the exact same time, x is 8. Now I have to figure out what y would have to be to make both of these equations work at the exact same time. So I can choose either one of these equations. I'm going to choose the top one. So if I choose the top equation, 2x plus 3y equals 18, I know what x is. X is 8. So I'm going to substitute 8 in for x, and I'm going to solve. 2 times 8 is 16. I subtract 16. I get 2. I divide both sides by 3. I'm going to get that y equals 2/3. So that's the solution. The solution is at the point 8 2/3. Again, x is 8, y is 2/3. At this point, these two equations are the same. They both work. They're both equal to each other. This is like if you were graphing. If you graph these two equations, they would intersect. They would meet at the point 8 2/3. That's harder to see with the graph because of the 2/3, but this is a different method for solving two equations, or really any number of equations, but a system of linear equations by adding straight down the line. I also get another example here. If we try to do the same thing here, I've got two equations. The x's are lined up, the y's are lined up. If I add straight down the line, don't write anything down yet, just wait a minute. 4x's plus 4x's is going to give me 8x's, and 7y's plus negative 3y's is 4y's. 59 plus 9 is 68. This is a problem. Neither of those variables have eliminated themselves. X is still there, y is still there. You can't solve one equation with two variables. You can't, it's not possible to solve for x and y with only one equation. We need two equations to solve for two different variables. By adding these together, we've created one equation with two different variables. We're stuck. We can't do this. So I'm going to move over to my document camera here for a minute, because we do have a method or a way to get around this problem, this issue that we have. So adding straight down the line didn't work. This is where I need to manipulate the situation. I need to change something. So I'm gonna manipulate this a little bit. I know that 4x and plus 4x is not 0. However, if this was a negative 4x, then I'd be set, because 4x plus negative 4x would be 0. So I first have to ask, what do I want this to look like? I want this to be a negative 1, or a negative 4, excuse me. So what I'm going to do is I'm going to multiply both sides of the equation by negative 1. So I'm going to multiply, because you can multiply both sides of an equation by the same number, and multiplicative property of equality, it works. And so the first equation, I'm going to leave the first equation alone. And if I multiply everything on both sides of this equation by negative 1, so I'm going to distribute the negative 1 through here, multiply the negative 1 here, I'm going to get negative 4x, negative 1 times negative 3, positive 3y, and negative 1 times 9, negative 9. All right, so let's see what happens when I do that. If I multiply everything through by negative 1, I get 4x plus negative 4x. That's 0 x's. The x's have eliminated. All right, that's so far good. 7y plus 3y is 10y, and 59 plus negative 9 is 50. Now I have one equation with one unknown, one variable. I can solve that easily by dividing both sides by 10, and I get that y equals 5. So by manipulating the second equation just a little bit, I was able to use this addition method, this elimination method, to eliminate the x's and solve for y. I'm not quite done though. I still need to figure out what x is. So I'll take the first equation again. I didn't do anything with that first equation. 4x plus 7y is 59. It doesn't really matter which equation you use. You could use the second equation here. You could even use the manipulated third equation, because these are the same thing. And I know what y is now. So I can solve for x. Minus 35, minus 35. I get that 4x equals, moving up a little bit, equals, what's that going to be? 5, 15, what is that going to be? 24, I believe. Yeah, 24. If I divide both sides by 4, I get that x equals 6. So my solution, x is 6, y is 5, and that's my solution there. Is that at the point 6, 5, those two equations are going to be equal or equivalent. That's how we deal with it if it doesn't work right away. If it doesn't work as it is, when you add straight down the line, we don't eliminate one of the variables. You have to manipulate that situation a little bit. So let's look at this one here. If I look right away, I can see that 2x plus 3x will not be 0, and 4y plus 5y will not be 0. So again, I'm stuck. Now this one is a little less obvious. Whoa. Sorry. This one's a little less obvious because I can't just change one of them to negative. They're both positive. And I am going to have to show all the work. I guess I didn't cover it up because I do want to go over to the document camera, and so you get a sneak peek. That's all right. I'm gonna look at a separate problem before we get to that one. So here's my problem: 4 halves plus 5/3. Now ignore the fact that 4 halves, you could reduce it. We're just going to look at this problem quick. If I want to add these two fractions together, I need to get a common denominator, the 2 and the 3. So I can always get a common denominator by multiplying the two denominators together. That's not necessarily the least common multiple, but it'll work. So if I do times 3 times 2, you don't have to write this down. You just have to watch. I would get 12 sixths, and I would get 10 sixths. And now I have a common denominator. So I can add these two together. To work with, or to combine fractions together, to add or subtract fractions, you need to have a common label. You need to have a common denominator. And one way to do that is to multiply those two denominators together. We're going to do the same idea. We're going to follow that same concept with this problem. If I want to eliminate the x's, or the y's, but I'm going to concentrate on the x's. If I want to eliminate the x's, I've got a 2 and a 3 here. That's not the same. I want them to be the same so that they can eliminate. One needs to be positive, one needs to be negative, but I need them to be the same number. I can use the same idea as I did with those common denominators to get a common number here. If I multiply the first equation by 3 and the second equation by 2, I'm going to get 6 and 6 here for the x's. So if I multiply through 2 by the second equation and 3 by the first equation, I'm going to get the same number here, 6 and 6. And again, the reason I need to do that is I want the x's to eliminate. They need to be the same number. I also need to have one of them be negative and one of them be positive. It doesn't really matter, so I'm going to choose the first equation to be negative. So I'm going to multiply the first equation by negative 3. I'm going to multiply the second equation by 2. Now let's see what happens. Now, after I distribute that negative 3 to everything and multiply everything in the second row by 2, I have a negative 6x and a positive 6x. This works for my addition method, my elimination method. Before, when it was just 2x and 3x, 2x plus 3x was going to give me 5x. X's did not eliminate. So I had to manipulate the situation by multiplying the two x's by the opposite coefficients. Multiply the second equation by 2, multiply the first equation by 3, kind of like a common denominator. I got the 6 and the 6 to be the same number. Those coefficients are now the same. I needed to manipulate it a little bit more to get one of them to be a negative. But now that I've done that, negative 6 plus 6 is 0. Negative 12 plus 10 is negative 2. 12 plus negative 6 is 6. Now I can divide and I can solve for y. So y is negative 3. I can now take any of those 4 equations, the original 2 equations, the 2 I've manipulated, doesn't matter which one. I can take any of those 4 equations and substitute negative 3 in for y. So I think I'm going to take the first equation again, just because we'll stick with it. And I know that y is negative 3. So I substitute negative 3 in for y, and I can solve. 4 times negative 3 is negative 12. Add 12 to both sides, divide by 2. You end up that x is 4. So my solution would be 4, negative 3. Now that was a lot of work. There was a lot of steps involved there. The big thing to ask is, if it doesn't work straight away, what can you do to manipulate that situation? What do you want these numbers to be? And then multiply to make that happen. You never add. You can only multiply both sides with the same thing to make that happen. But manipulate that situation to make it work the way we want it to. I'm going to ask you to try these two on your own. If you haven't paused it yet, pause it, try them. I'm assuming you tried it. I'm assuming you worked with these problems, manipulated things to make it work. Here are the solutions, and I will show how to do those in a separate follow-up video.